Okay, so for today's session, we will go through topic number 4-3, which is continuation of bridge analysis, but with very specific method to calculate what's called live load distribution factor. Last lecture we spent in the class spent time to go through all the live influence line to get the moment and shear and maximum reaction for moving trucks. So I'm gonna start the first maybe 15 slides, just refreshing on the loads. So today's should be the last sessions on topic number 4-3. We will also, I'll decide that later on, but next lecture will be in person, which is going to be on Monday. I will also do a hands-on on this topic so we can have in-person connection too. Just to recap what we have on the loading, I'm pretty sure that I can now call on you guys and maybe have some discussion. Josh Bizillo, can you tell me which table is this? What did you use with this table?
Yeah, can you hear me?
Yes.
So this table is used when you're trying to determine the cross section of a bridge. You need to know the depth of that section. So what this table allows you to do is convert the length of the bridge into the minimum required depth, including the deck that you'll need to actually design the bridge for.
Okay, that's great. And this based on different material and different superstructure types, correct?
Yeah, you can do it for reinforced or pre-stressed concrete, and then steel is at the bottom there, and it will give you both the depth of just the I-beam portion and then the depth of the entire
Sounds
bridge.
sounds great. Thank you, Josh. So I'm gonna call on someone else now. Adam, I'm just calling randomly, okay? In this slide, did we do something similar for this problem before or not in any homework?
I remember kind of seeing this a little bit in like homework 2 and a little bit of homework 1 where we made the what's it called? Oh my gosh, the cross section of a CIP girder and also just a steel girder as well for a bridge. So this is pretty familiar, yeah.
Yeah, so this one you have the girders spaced as different spacing, correct? You have interior stringer and exterior stringer, which is girders or beams. We also discussed having the overhang, right? Remember, Adam, what's roughly was the overhang length in in terms of the spacing? Can you hear me, Adam?
Can't remember right now, but I'm gonna try to look at my notes.
Okay, that should be fine, but it should be something between 0.4 to 0.5 s, right? The spacing between the girders. And we also know that we have to get the haunch, which is the concrete part that make the transition between the girder and the bridge deck. You have the slab, which is often we talk about it as bridge deck. You have the rail. Sometimes you can have sidewalk, so pedestrian can walk here. And you also can measure the out-to-out distance. And you also have the clear roadway distance, which is from the sidewalk to the sidewalk. So our purpose today is, if you remember last week, we did the analysis of the bridge in the longitudinal direction for moving load. Today, we will do it in the transverse direction, assuming we have in truck. And our goal is to see how much percentage of the weight will go for each girder, the interior girders and the exterior girders, okay? I'm pretty sure if I ask Allison to maybe comment on this slide. Do you have any comment, Allison, on this slide?
Well, this slide details some of the different loading on the bridge. You have the dead load of the structural components and the non-structural attachments. You also have the dead load of the wearing surfaces and utilities. And then the vehicular live load and the vehicular dynamic load. Those are some of the loads that we've been talking about in class the past couple weeks.
Okay. The only thing, yeah, thank you, Allison. The only thing is different from the last few weeks is that we have something now called DC1. I don't discuss the difference between DC1 and DC2. There is some verbiage here, what's the difference between DC1 and DC2, but if you assume you have a steel girder, assuming this is your steel girder, right, and you have a bunch of them, correct? And you have bridge deck that you're gonna cast a concrete into using a formwork maybe here between the girder, and the weight of the concrete, because concrete is still gonna be wet, will be transferred to the girder, correct? And the cross section is just a steel cross section in this case. So the DC1 is for anything, any dead load that actually act over the girder cross section only. Okay. However, after 28 days, concrete is cured. Now the cross section became also called composite sections. So if you cast something later, maybe the concrete rail or barrier, this will act on a composite section. So steel and the slab will act compositely. Do you guys have any question in this difference between DC1 and DC2? If you don't have any question, I'll move forward to the next slide. I'm gonna call on Cedric. In this slide, do you remember what table is this one and why we use this table and which function of this table to be used? Cedric. Are you muted or? Okay, so he has microphone trouble. I'll say John McCleary.
So we can use this table to get the different load factors depending on like what type of like, for example, like the extreme events for different like parts of like the bridge.
Okay, so what you're saying is you have load combination from strength to stream event to service to fatigue, and based on this table, you can get the loading factors, right, for each type of loading, correct?
Yeah.
Okay, so, thank you. Isa, do you remember this table or not? This table 3.4.1-2.
Yeah, table 3.41.2 is the ASTO load factor. So we basically get the load factors for different kind of loadings and different kind of applications, depending on strength and the strength and the what component we're trying to model the load on.
Okay, so from previous, if you go back one slide, you will see gamma P, right? So there's no number in this table, correct? And this table in 3.4.1-2 is giving you those values based on your DC, DW, etc. Correct?
Hmm.
Okay, Hamdi, do you know why we have maximum and minimum here?
I believe it's gonna helpful if we have a multi-span or continuous beam. For example, if we have a bent with having overhanging. So in this way, we have to use for dead load. If we need to consider the maximum bending moment. So
Okay. So what you're trying to say here is if usually we use the maximum values
yes,
if the moment sign or the shear sign of the dead load and live load are the same. And if they are opposite, use the minimum for dead load so you can maximize the effect of live load, correct?
yes.
Okay, thanks, Hamdi.
Thank you.
I want to choose from here. Joseph Kyle. Are you familiar with this slide, Joe?
Yeah, this is the design truck that we've been talking about, HS20, and it gives the applied loads onto the pavement at each axle. So front axle, both wheels weight adds up to 8 kips. It gives a spacing of 14 feet, and then the next axle is 32 kips, and then the back axle is also 32.
Okay, what is the distance between the two lost axles? Yeah, I'm gonna make, yeah, here is the cheat sheet, right?
Yeah, between
Yeah.
14 and 30.
30, correct. Okay. Thank you. This is good. Matthew, so we have the axle distance are 14 for the first two axles, and the last two, the second and third, are between 14 and 30, correct? So what is the distance between the wheels?
Would be 6 feet.
Correct. Okay. And what is the total width of the truck?
Would it be 10 feet?
Okay, so you already, yeah, so it's here and there, right? So if I move to the next slide with you, you will have the truck width is total width is 10 feet. The wheel distance center to center are 6 feet, right? And you have 2 feet to the curb and another 2 feet to the end. Anyone just voluntarily can tell me what is the design lane width? Or should I call them people?
12 foot.
12 feet.
Okay, good. So the lane itself is 12 feet, right? So if you start the lane from here, you actually have freedom to move the truck within 12 feet width, right? However, the truck itself is 10 feet, correct? This is a design truck HS 2020, but this is not the design that we use. We use which one? Let's ask Anthony McKay. Can you hear me?
Yeah, are you talking about the one we use specifically in New Jersey?
No, there was there is HS20 and there is other component, right? Design tandem, right?
Oh, okay. Yeah,
And
sorry,
there's
I was
something
thinking too far.
Yeah, something you need to add to in order to make it the design loading, right? We called HL93, right? HL93, correct? So so we have another one. Manjit, are you online?
Yeah, I'm here.
Yeah. So for the design tandem, right?
Mhm.
What can you say about it, like in terms of axle, wheels, etc.?
Um, well, the way, like, just for like the loads or just how it's designed?
Like what kind of load, how many axle, distance between the axle, distance between the wheels, etc.
Oh, so so like the total weight of the vehicle is 50 kips, and the total axle weight is 25 kips, and the spacing
This is 25 and this is 25, right?
on both, yeah,
Yes. And the distance between them is 4 feet.
yeah, 4 feet, and like we
And-
said earlier, the distance between the wheels is 6 feet.
Yeah, and the total weight is 10, so that should be fine. Back to we have also component called lane load. Moria, can you tell me why kind of we have those live loads, lane live loads, uniform loads?
What was it? Why can't we have live loads? Was that the question?
Why we add live loads? Like
Oh,
it
it's
yeah.
the trucks, like, they aren't parked on the bridge, they're moving, so you add a live load or a load of the distribute load of the bridge.
So if you have the main truck, right, correct? This is in longitudinal direction, correct? You assume that you have a convoy of trucks before and after and even underneath, right? Because to get the same effect of the typical trucks on the bridge, correct? Okay. I just want to choose someone else. Shandur, Shandur, what kind of truck this one is? Last time I think you were in the class, correct?
Yeah, so this is,
Yeah.
well, the slides say it's a permit truck.
Yeah, for which, do you remember which state is this one? It's really tough to remember.
No, I don't remember which state. I just remember that it can vary depending on which state you're looking at. There's different standards for them each.
Which state in your project is?
Louisiana.
Okay, so this is for New Jersey, okay? So that means that you don't, like, if you don't remember, it's fine. So this is based on the permit truck that each state allow in their highways, and in this particular case, you have so many axles. I think it's 8 axle here. Starts with 16 kips. Front one, 12 feet to the second one, and you have another 16 kips, and then a series of 28 kips is spaced at 4, 4 to 1, 4, 4, and 4. And we used this one, I think, in one of the example last week, correct? Okay, so this is for state of New Mexico. And this is the P5, P6, P9, P11, P13 for California. If I ask Walter Ford, do you remember or have any guesstimate why we call it 5, 7, 9, 11, 13? Okay, number of axles, correct. So it looks like he has some issues with his microphone, but if you have P5, you have 5 axles. This is B5, so P7 will be this one. P9 would be this one, and so on so far, P11 and P13. We mentioned that we have to use dynamic load allowance. William Bright, do you remember why actually we have to use dynamic load allowance?
Does it have to do with the moving load across the bridge because it's a live load?
What feature that moving load can influence the bridge?
Can you repeat that? I'm sorry.
What kind of feature? Why we need to use that? What feature that moving load can affect the bridge?
I'm not too sure, to be honest.
So if your truck is a weight at the end of the day, correct?
Yeah.
If this weight is moving very slowly on the bridge, it's gonna be having the same effect if it's just moving when it was 50 or 70 mile per hour?
It'd be more of effect if it's moving slowly across, right?
So which one is higher, slow or
Slow speed would have more of effect.
slower or higher?
Higher, I'm sorry.
Yeah, so why higher? Because you have dynamic effect, correct? So your truck is interacting with the bridge and you have a dynamic component to it, correct?
Yeah.
So that's why we use dynamic load allowance in order to magnify and take into account the dynamic effect of truck moving at a speed, correct?
Mm-hmm.
And for your information, this question will be in your midterm exam, okay? Not exactly, but something in this regard, okay? I want to ask William Caracas. Can you hear me?
Yeah.
This may be a tough question, but maybe you can give it a try, right? We usually use 33%, right, for dynamic load allowance IM, correct?
Yeah.
To amplify the truck loading, correct? However, it says here for deck joints, use 75, correct? So if we are using all other members and components for all other limit state, we use 33. And for deck joint, we use 75. Do you know or have any guess why the deck joint will take more or will be designed for more than others?
Because the joints are more likely to fail, so you need some.
And it's more likely impacted directly by the truck, correct?
Yeah.
Because if you have a bridge, the load has to move from the deck to the girder and maybe substructure, correct? However, the first contact with the truck will be the closure, the bridge deck joint, correct?
Yeah.
Okay, that's actually a nice guess. Peter, can you hear me? Peter, you're muted. No, I can't. You're muted. Maybe Mohammed, there is three sentence here. There are three sentence here. Can you elaborate on them? Just reading and give some feedback. Can you hear me? You guys can. If Mohammed has, I think, has issue with his mic too. Kyle Ring, can you hear me? Can you guys hear me?
Yes. Yes.
Yes. Yes.
Okay. I'm not sure if maybe they are having hard time with mic. Maybe go to Jake Peterson. Can you hear me, Jake?
Yeah, I can hear you.
Yeah, so you can see here, the answer is in the slide actually, but if I ask you which component of the design that we have to apply dynamic load allowance, IM. So you have design tandem, right? And the design tandem is 25 kip each axle, correct? And you have the design truck, which is 8, 32, and 32, right? And you have lane load. Which one of those three we apply dynamic load allowance to?
Believe it's the live loads, if I remember correctly. I guess
Which
probably
part of the live load? It's actually it's here. Actually, you can read and cheat.
So the actual, so everything but the design lane. So the actual weight of the wheels on the road.
Exactly. Whatever has axle when you draw it, correct?
Right.
When you draw your loads, if you have axle, I have to multiply times IM. Okay. So the design tandem and HS20 and permit truck, but not the uniform load, right?
Right.
Design lane. Okay. Maybe asking. I'm not sure if I ask everyone. It looks like I forgot something. Gary, here, can you hear me?
Yep.
Can you tell us a little bit about what is multiple prism factor, if you still remember from a few sessions before?
Yeah, so as we discussed above, the design lane width is around 12, well, is 12 feet. And
Okay.
we want to try to fit as many of those design lanes into the actual length or width of the bridge cross section as we can, from going from the rail of the barrier to the other rail of barrier. And we'll fit those 12-foot design lanes next to each other as closely spaced together as we can. And it would be the loading of the design trucks on those lanes, and we'll do it in like 1, 2, 3, and each amount of lanes loaded would have a specific factor attributed to that. And there is special you have to do stuff special for bridge widths that are between the 20 and 24-foot widths that can take 2 design lanes, as they'll be reduced to like 10 foot.
You actually answered another question, but you answered it very well, so it should be fine. You answered like a future questions, but the multiple prisms factor is a factor that you have to use when you have the design lanes. For example, if you only assuming one design lane and the rest of the bridge will be empty, this is less likely, high likely to happen, correct? That you will have a truck, only one truck on the one side, maybe small cars on the other side. So we actually, because of probabilities, we should increase the load by 20%. If we have 2 trucks side by side and the rest of the bridge is just vehicles, this is likely to happen. So we don't amplify it. If you have 3 or more, 3 actually, this is really rare to have 3 trucks side by side over the bridge, the same location. That's why we reduce the load by 15%. And if you have more than 3 lanes, you actually reduce even further by 35%. Any question on multiple prism factor? Okay, John, can you hear me?
You're talking to me?
Yes, John
Okay.
Verbal, right?
Vrabel.
Yeah, variable. Sorry for misspelling. If I ask you a question, if I give you 60 feet width of driveway or width of drive, which is from barrier to barrier, I give it to you as 60 feet. How many design lane I will have on this bridge?
Do you make it 4 design lanes? Loaded lanes? Or
4 lanes will give you how much width?
48?
Okay, 48. How about 60? 60 will give you what?
Well, then when I go to the end of the bridge,
I'm saying like
each side would be all the way to the end of the actual width.
Yeah. So this distance, if I assume this distance is 60.
Okay, so 5.
5, correct? So the easy way to calculate it is just to get the distance from edge of the barrier or the rail to edge of the barrier of the rail and divide it over 12, correct? And now, when you have 5, you have scenarios where you have 1 lane only, 2 lane only, 3, 4, and 5, correct? 1 lane loaded, 2 lanes loaded, 3 lane loaded, etc. Correct? I want to call on someone, but maybe this is gonna be another question, but this question will be with bonus, okay? If I have a bridge that looks like that, okay? And I have intermediate barrier. So I have some girder there. And the total width from the exterior barrier to exterior barrier is 60 feet. And this is around maybe 4 feet, this interior barrier. How are you gonna start layouting your design lane? How many design lanes do we have?
2 lanes in each side.
Let's
So total 4.
maybe just chat, respond to the chat box and write directly to me only. How many lanes each one of you think will be on this bridge? Respond to me privately. Okay, looks like we are. Looks like we got almost everyone responding. It's actually we have either 4 lanes or 5 lanes. This could be the answer. It depends on if this barrier is permanent or not. If this barrier is actually cast in place with the bridge deck, so there is no way that you can later on move this barrier off the bridge, this barrier will actually split the bridge to 2 distances. 60 minus 4, which is 56 over 2, make it 28 here and 28 here, correct? And now you can have 2 trucks or 2 lanes, 2 design lanes of 12, correct? In this side and another in the other side. However, if this barrier is removable, they can actually move it in other way to do traffic control or something. So this barrier can be unbolted and removed. Now you design for 5 design lanes. Okay. Any question on this one? If you have any questions, most of you got like 4 lanes answers. Go ahead, Hamdi.
I want to ask if we have this case for lane.
Okay.
So what about the presence factor? Is it gonna be 2 per each direction or gonna be 0.65?
For what you say, you put the two here and 2
lane per each direction.
Yeah. So you will do 3 or more.
So it's gonna be 0.65.
Yes.
Okay. Thank you.
Any other questions? So you can expect in the exam, like just like a question is like very, very conceptual. It's not just it's not gonna spend like 2 minutes to answer it just to get the right dimension and see if the barrier is permanent or not. And there is but this is the heart of this class is in this lecture is you have to know what distance you are measuring. It's from exterior barrier edge to exterior barrier edge. If you don't have any permanent barrier, just take this distance, divide over the design lane width, you will get your number of design lanes. And you have to load them one lane or two lane loaded, three lane loaded, four, etc., to get into the live load distribution factor that we discussed earlier. We're going to discuss actually after a few minutes. Any questions so far? If no questions, I'm going to keep moving. This is the same. Same image or photo. What you need to do is you have the bridge. You have to subtract from the total width, the barrier width. You will get whatever distance from edge of the barrier to the edge of the barrier. And you divide by 12, you get rounded down to 3 lanes because you are not able to put another lane here because the distance here is less than 12. And in your case, in this bridge, you have to do one lane loaded or 2 lanes loaded or 3 lane loaded. Okay. And you need to really make a difference between where, what is a design lane and what is a layout of your bridge girders. They are not related to each other. So before in assignment 2 and 3, I didn't mention anything about the design lane and how the truck will move over the bridge, but I ask you to lay out the girder, correct? So that's why they have no relation. So you cannot say I'm gonna put the girder here because the truck will be here. No, the truck can be anywhere along any direction, in any direction in the transfer direction, any location in the transfer direction. And it is just a sketch of what's called bridge loading that we do sometime for bridges. We bring those loading trucks and we put the weight on them, maybe sand or whatever, and we put them side by side to simulate three lane loaded case. But as we mentioned, because of the multiple presence factor, they are not actually, it's not, probability of having them side by side is less than having one or two side by side. So I need someone to interact with me. Anyone can volunteer just interacting with me on this slide? Raise your hand, maybe. No one is trying to interact. Isa, you always ready, right? Isa.
Yes.
I want to have a discussion with you on how we should start layouting the wheel, actually, right? Because we agreed on the longitudinal direction, correct? We have axle, right? For example, for HS20, we have 8 kips, correct? And we have 32. And we have another 32, correct? This is in the longitudinal direction, correct?
Yes.
And the distance are 14 and 14 to 30, correct? And we did the influence line last time in order to get the moment and shear, correct? So in this today, we are considering the transverse direction. So we should actually consider the wheels, correct, in the transverse direction of the truck. We have the wheels, correct? Can you tell me what is the weight of these wheels?
Would we take the?
So
do you want to include the dynamic loading or just like the as a point load?
Just as a point load. Can you figure out what kind of this load and this load? assuming this is your load P, which is total. The total load is 8 plus 32 plus 32, correct?
Mm-hmm.
Which is give you 72 kips.
Yes.
So how much in this direction will be this load here and this load here? In terms of P.
Should be P over 6 if it's 6 wheels.
It's actually, if I assume it's P, it's gonna be P over 2 here and P over 2 here, but you're correct, because those axles actually, as part of each, sorry, those wheels are part of each axle, correct? So you will have like 8 divided by 2, right? So you have 4 here and 4 there for the first axle.
Yes.
Correct? What about the second axle?
It's going to be divided by 2 wheels.
So how much?
16 each.
16 each, correct? And the last one, third axle.
Same.
16, right? So if you are working a lot with LiDAR, right? So you have, if you have a segment here, correct? And this segment is moving along. Once you reach the axle number 3, you will be there, right, at the third axle, correct? So the loads will be 16, 16, correct? And it moves us to a second one, 16 and 16, correct? First one is 4 and 4. Because now we are not considering the longitudinal direction, we are only care about the transfer direction. We can safely say we can smash all those axles together and represent it as P over 2 and P over 2, and P is actually the weight of the truck.
Okay.
Right? Because the influence line will take care of the distance in the longitudinal direction, correct?
Right.
So now I can safely say this axle, this wheel is P over 2, right? And this is P over 2. Okay. I need another volunteer. Thanks, Isa.
You're welcome. Thank you.
Should I call on you guys? Alisa.
Hi.
Can you hear me?
Hello.
So we discussed last time that the width of the truck is what? 10, right? 10 feet.
Yep.
So in order to start layouting the lane loads, right? We start from the edge of the barrier, correct?
Yes.
We place the first wheel. How far from this distance?
The minus the 4. 2 feet, I think. 2 feet or 4? 2 feet. 2 feet.
Because if you go back in the cross section, they are 2 feet, right?
Yes.
From the curb, right? So 2 from the curb, 6 center to center, and 2 to the end of the width, correct?
Yes.
So now we can put 2 feet, which is here. We put the first P over 2, right?
Yep.
And after that, we put another distance. What's the other distance?
6 feet.
6 feet. You put another P over 2, correct?
Correct.
And after that, you have 2 feet to the end of what? Of your truck width, correct?
Correct.
This gives you 10 feet, right? However, your design lane is what?
12 feet.
12. So you will have like a gap between the two trucks, right? Because you cannot have the truck touching each other, right? Driving without distance, 2 feet at least.
Yes.
So after that, you start putting the first wheel for the second truck, which is 2 feet, 6 feet, and another 2 feet, right? I give you 10 feet, correct? And this lane is width is 12, correct? Which ends here. And so on so far, right?
Yep.
So if you ask a question, what is the distance between the wheels?
Between the wheels, it's
Yeah.
6 feet.
Yeah, it's always going to be 6, right? Because they
Yeah.
are 6 always. And even if you have 2, you have gap of 2, and you start another 2, so they are also 6.
Oh, 6 feet.
So you can start 2 feet from the curb, right? Or the barrier, and just putting the wheels at 6 feet, correct?
Mm-hmm.
And those distance should be 6 feet. This is great. Thank you, Elisa.
Thank you.
Any questions from everyone? Anyone? I know it's in person is easier to see the reaction here. I cannot see faces, but if you have any questions, just maybe raise your hand or interrupt, please. So if you don't have any question, here how we lay out our trucks in transfer direction, correct? P over 2, P over 2 for each of those arrows, and they start 2 feet from the edge of the barrier. You put another 6 feet to the second wheel on the first truck. And after that, you have 2 feet gap, and you put another 2 feet to the first wheel of the second truck. Distance of 6 feet. And you put the second wheel of the second truck. Distance 2 feet to end your truck. You have 2 feet of gap to start your third truck. You put 2 feet to the first wheel of the third truck. 6 feet. You put the second wheel of the third truck. You have 2 feet to the edge of the truck and 2 feet gap. May I ask some question and answer to me in the chat? Can we have odd number of wheels on the cross section? I need answers. So looks like most of you guys agree that we can't have odd numbers of wheels on the bridge. Anyone can volunteer why? Yeah, Walter said because it may have, you may need to have. Go ahead, Chandra.
I was just gonna say, even though like you can consider like motorcycles or something like that, but if you're designing for a truck, it would still be more conservative because it would account for more.
Yeah, you cannot do odd number because you don't have a space to fit entire truck, correct? You cannot just fit one wheel. And the loads are very considerably high, right? 32 kips, 8 kips, and 32 kips, right? So you may allow, vehicle or motor or bike or whatever to drive, but they are not significant, correct? Okay. So this is actually good discussion. I just want to say, if you are paying attention today, ask so many questions. Those are meets for midterm exams. So you will have some of those questions on the exam. So the good news is also that you have maybe the recording, so you can go back and you're gonna post the recording of this session later on. Do you guys need to have like maybe 5-minute break? I know that we have 2 sessions today, but let's have 5-minute break and come back 7. Let's say 7-minute break, 7 to 7:30. So 7 minutes from now. Stay online. Stay online. Don't leave the. Lisa, go ahead. Lisa, are you raising your hand?
No, that was my mistake. I'm sorry.
Oh, like 50 minutes ago or something.
Yeah, it was when I answered to volunteer and I kept it on.
Okay.
I'm sorry, my bad.
Any questions from anybody? Okay, we'll resume in 5 minutes, 6 minutes. Yeah, let's resume. So as we discussed, I think up to the last slide, most of the information are just refresher from previous presentation and lectures. The goal here now of this session is if you have a steel girder or concrete girder, whatever type of girder you have, and you have a bridge, let's say you have 4 girders, and you have your bridge, whatever the bridge looks like. Sorry, I'm just drawing with very bad way, but here is your bridge, and this is your barrier, and this is your barrier, correct? If you find that it's 2 lane, a maximum of 3 lane can be loaded, you can study the first lane and see, you put your wheels right here and there, and this is gonna represent P/2 and P/2 of the truck, correct? In the transverse direction. Our goal now is to know in these circumstances or location, how much of the load will go to this exterior girder as percentage of this truck, how much will go for this girder, how much will go for this girder, and how much for this girder. And if you add another truck side by side, they're going to be two lane loaded, correct? So the other scenario will be how much of those 2 trucks, of a weight of those 2 trucks will go for as factors to this girder, and this girder, this girder, and this girder. And this is what's called live load distribution factor, LLDF. We have 3 methods. The first one called labor rule. Second one is called simplified equation by Ashto. Some of the equation is never simplified, but they call it simplified equation. And the last method called special analysis method. Okay. By the way, how many of you did watch the video before joining today? Can you just say yes or no in the chat? So we have like 2 or 3 no. Rest are, aren't able to watch. No. Okay. Okay, anyway, but if you watch, you may have questions, but if you then, I don't think you will have up to now, but let's keep going. And if you have any question, please interrupt, okay? Raise your hand or just interrupt me, okay? So the first method called lever rule. The lever rule is a method that I just want to minimize this as possible. So not sure I can do that. Yeah. So assuming you have in the cross section whatever number of girders, like let's say you have 6, 5, or 5 girders, whatever. Okay. So this method actually says that you have to assume a hinge in every intermediate girder. So that will act as like series of simply supported beams. And as you can see here in this example, the assume hinge, if this is your second intermediate girder, and this bridge is only 3 girders. So this is exterior girder, this is exterior girder, this is interior girder. You assume a hinge here, okay? And you solve with a static principle and get the reaction on the exterior girder. So most likely this method is used to calculate the loading factor, live load distribution factor for exterior girder. So assuming if I have let's say who's here online? Anthony, are you online? Anthony McCain.
Yes, I am.
So assuming, I'm just selecting randomly, but assuming that you have a bridge deck here, okay? This is the sky blue, right? And I maybe have a barrier here, and the first wheel, which is half P, right? Exactly was located on top of the exterior girder, okay? And the second wheel is actually 6 feet away, right? As half P. And the spacing between the girders are 9 feet. If I assume there is an intermediate hinge here, right? Or assigned hinge here, can we calculate the reaction on the exterior girder, RG1?
Yeah, so we can just do like a basic statics problem where we can take the moment from
Around this hinge.
from
Okay,
from the interior girder.
can you spell out the equation for me? Like this load, this wheel load, right, is 0.5 P, correct?
Yes, and that would be 9 feet away from that interior girder.
So this is 9 feet away from the interior girder, correct? This distance here to there, right?
Yep.
Okay, plus.
Then plus another 0.5 P, and that would be times 3 feet.
So 5 P times 3 feet, which is 9 minus 6, correct?
Yep. Yep.
Which is this distance, correct? 3 feet. And this should be equal what?
It would be the reaction on the exterior girder, so RG1 times 9 feet as well, since that's also 9 feet from the interior girder.
Yes, so this is 9 feet. So if I rearrange the equation, I can have RG, if I take half P as common factor, right? And at the same time, I divide over 9. So 9 here became 1, 9 here, 3 over 9 became a third, right? And I take 0.5 P as a common factor, right? I have 1, which is 9 over 9, plus 3 over 9, correct? Which is a third. So the load will be 0.667, which is 2/3 of a P, right? Correct, Anthony?
Yep.
So what does it mean if 2/3 of the P goes to the exterior grid?
So that would be, so you have I guess the 0.5 from the one wheel, and then you would have I
Yes.
guess another
Portion of the second wheel, right?
yes, it would be another portion. It wouldn't
So-
be, it would be less than half of it, but it would probably
Okay,
be what, yeah.
because this wheel is closer to this, right?
Yes, yeah.
So that means that if I have a loading scenario where I have one truck very close to the exterior girder, right? I can consider in this case 2/3 of the truck load or weight will go to the exterior girder, correct?
Yep.
And this is actually not counting for, I'm still not counting for multiple present factor, right? In order to count for it, I have only one truck, and the factor for one truck is 1.2, right? So you have to multiply this factor times 1.2 to count for multiple present factor. Correct. Any questions so far on what is lever rule is?
Can this only be used if there's 3 girders? What if there's more?
No, it doesn't matter. If you have so many girders, you only use it to calculate it for the exterior girder only. Okay.
If there's an even amount, like there's 4,
yeah,
the hinge would still be in the middle.
What do you mean by 4 girders? Let's say like I have a bridge with 4 or 5 girders.
Yeah, like see how this one has 3, so the hinge is right on top of the middle one. What if there was an
Yeah.
even amount, like 4 or 6? Would the
You
hinge
see
be
that?
in between the girders?
You see this sketch here? I'm drawing around the circle. How many girders do we have?
But what if there's 4?
1, 2, 3, 4, 5, actually, right?
Right, but what if there's 4?
Yeah, you always assume that all the interior girders will have hinges. So your hinges will be in the interior girders.
I think she's asking if there's 4 girders specifically. So because you'd have 4, the middle of the bridge wouldn't necessarily have a girder right in the middle of it. It would be offset per se. So you would necessarily wouldn't have a hinge directly on that girder.
That's what I'm asking.
So you see what you're saying is if you have a bridge like that, where your hinge will be here? Where are you going to place your hinges?
I'm asking you.
On top of the girders, interior girders.
Always on top of the girders. Okay.
Yes. So it doesn't matter where they are, how many they are. In top of the girder, just place the hinge. So in another way, that it's actually a series of small, simply supported beams, right? Right? Did this answer your question?
Yes, thank you.
Thank you. Any other question? If you don't have any question, can you solve for me if this distance is 10 and this is 10, okay? And this axial load is actually 1 foot away from the exterior on this side. So you start from here, 1 foot, and you count the 6 feet from this point, right? Now, how much will be your multiple prison factor? Live load distribution factor, sorry. Just take a couple of minutes, maybe sketch something and send it in chat. Any answers? Are you guys done or still calculating? Walter, I love how you are accurate. You said, without multiple present factor, which is great. Good job. Any new answers? Okay, so it looks like you guys get Juan is not 0.7, it's 0.8. So check your answers. And the second girder will be 0.2. I have a question. Let me ask Jack Peterson, why we have the girder 3 0? Yeah, I'll go over it, John.
Girder 3 is 0 because the hinge is there. It doesn't.
Is there, and there is no axial loads. There is no axial load, sorry, wheel over this pay, correct?
Right.
So all the loads either goes to 1 or 2. If you have this load is crossing, actually, right? That means that this part of the axle will go to 2 and 3, will not go to 1, right?
Right.
So let's go and solve it, because looks like some of you guys are confused over it. Okay. So I got wrote here. Maybe go back. I don't know how to erase it, but if your second girder is this one and the exterior girder is this one, correct? The distance here is 10 feet, correct? And you place your first axle, or actually wheel load, 1 foot off center to the left of the exterior girder, and this is half P. The second P will be 6 feet from this point, which is, all right, 6 feet here, or actually 5 feet from the exterior girder, right? Because you have 1 foot here. Now we have another half P. Now take the moment around the interior girder. You can write half P times the distance. The first wheel is at distance of 11, 10 plus 1 plus half P. Second wheel is around, it's 5 to this exterior girder, so it's another 5 here because the spacing is 10. So this distance is 5. And the reaction on the exterior girder will be times 5. RG1 is at, sorry, distance 10. Correct? The distance 10. So 11 is times half is 5.5 P. Half times 5 is 2.5 P. And the reaction is 10 times RG times 10, right? If you add 2.5 and 5.5, give you 8 P. You divide over 10, RG1 equal 0.9. Any questions? Jean, you got it now?
Yeah, what was the 8/10? Is that P?
Which one, 8 over 10? Yeah, it's 8 is when you add those up, right? 2.5 and 5.5. And
Okay.
multiply by 10, right? You got RGP, right? RG1, right? So it's 8 over 10.
All right, thank you.
Right. Yeah. Any other questions? I saw like few of you actually got like 1.75. I'm not sure why, but maybe equal 0.7 because of maybe offset numbers or something wrong in your calculation. But this is how it should be. Let's move forward. There is one parameter here we need to calculate. And it's very important to know. It's called stiffness parameter, right? If I ask someone to volunteer, this girder, steel girder, did we deal with it before in calculating the inertia and area? Can anyone volunteer answering? Which homework was that?
Yeah, we just we did it for assignment 3, and it was lecture 4.1, the first part of
Yes.
the.
Yeah. If you have a steel girder, you can come up with a table that you can calculate the thickness of each plate, width of each plate, and the areas, and it's, you know, complete the table to get the inertia and the area, correct? So if I give you the inertia and area, or you calculate it, and you have the modulus of elasticity of this girder, if it's steel girder, the modulus of elasticity will be ES. If it's concrete pre-stressed, will be EC, right? So in this case, I have also the modulus of elasticity of the bridge deck. So we have terminologies here, right? We have modulus of elasticity of the beam material. It can be steel, it can be concrete pre-stressed, or modulus of elasticity of deck material can be most likely concrete. We have the moment of inertia of the beam that we calculated before, and we have the area of the beam, and we have a distance called distance between CG of the beam to CG of the deck. So once you have the CG of your beam and your CG of the deck, you can get the distance EG. And you can go for this equation and calculate what's so-called the stiffness parameter Kg. The stiffness parameter Kg equal N times I plus A times Eg to the power 2 or square. So we know inertia, we know the area, we know the E value, which is the distance between the centroid of this bridge deck to the centroid of the girder. And the only thing we need to know is N is the modular ratio, which is the ratio between the modulus of elasticity of the girder to the modulus of elasticity of the bridge deck. And this one, you have to get integer. So if it's 7.9, you take it integer as 8. And if it's 7.1, for example, you take it as 7. So it has to be integer number. So why you ask us to calculate this parameter Kg? This parameter Kg, if you think about it, it's as we take the moment of inertia of the girder in respect to the CG of the bridge deck. So it's area times Eg square plus inertia of the girder times N to convert from steel to the deck material of concrete, for example. So if as we smoosh the girder material and properties and apply it, smear it here somewhere. So your all girder, as for example, converted from girders to a smeared material at the level of the deck. Right? That was called stiffness parameter Kg. Any question on Kg definition?
So is it just effectively getting the stiffness if it's a composite section?
It's basically if you want to have this girder, assume this girder, you can have it at the level of the bridge deck with the effect of the stiffness and area of this girder. Okay?
Makes sense.
So that way your girder are smooshed or smeared at this location. Okay, so this kg is important when you calculate the factors, which you're gonna go later on. Remember, last method we did was with lever rule, right? We did the calculation. The second one is what we call simplified equation. Before we go to the simplified equation, in order to go to a simplified equation, we need to understand what is kg parameter is and what is distance dE. The distance dE is the distance between axle load, or this is a line of axle, right? So like I have 3 axles here, for example, which is a wheel, right? And the exterior girder axles. So the axis of the exterior girder to the wheel location, the first wheel location, this distance we call dE. And we also need to know the parameter like girder spacing. You have girder here and girder there. So this is a spacing. We also need to know parameter called slab thickness, which is we always know, which is TS. Okay. And the span length. If you have a bridge with a span length, you have L. Okay. So all the parameter we need to know is kg. We get it from the previous slide. We need to know the span length, or sorry, girder spacing S in feet, which is previous example was 9 or 10 based on the problem we solved. The thickness of the bridge deck is this distance in inch. And we need to have the spacing is span length, which is L in feet. Okay. And the dE value is the distance between the first wheel to the center of the exterior girder. Okay. So in order to do that, you need to identify for your cross section after you lay out your girder and lane loads. You need to identify the kg value, the S value, the TS value, the L value, and DE value in order to use the simplified equation. For the simplified equation, if you go to ASTO, you have a table, I call it the legend table, the legend. So table 46222, sorry, 46221-1, it gives you like a legend for every cross section. So for this cross section, they call it cross section A. It supports the cross section is supported by steel beams, right? Correct. And the bridge type or bridge deck type is cast in place concrete slab or precast slab or whatever other options. So if I ask you in your problem number, the homework number 1 and 2, when I ask you to do the box girder and the steel girder, right? Cross section. In the steel girder, which type of cross section you have? A, B, C, D, E, F, G, H. Which one? Isa says A, Shandor will say A, Jean A, Joe A, Adam A. Yes, because we have a steel beam carrying cast in place girder, right? If I ask you about the box girder, okay, which cast in place, if I ask you about cast in place concrete box girder, which section should be? So yes, cast in place concrete multi-cell box, and the concrete is monolithic, right? So the answer should be D. So this is called a legend because it gives you what kind of cross-section letter that you need to use for another table. For example, can someone tell me what about if you have the girder as precast? Which section is this? It's not this one, right? It's not A. It's not steel. Closed steel or precast concrete boxes. It's girder, not boxes. It's not this one. It's not this one. Open steel and precast concrete boxes. Not this one. Cast in place concrete multi-cell box. Not this one. Cast in place concrete T-beam. Not this one. Precast solid void cellular concrete. Not this one. Precast solid void. No, this one. Do you think, guys, it's the edge? Nope, because it's a channel. Channel means that your cross section looks like that. And you can see it clearly, right? They're having like two legs here. So where's the R? The actually section number K here, because the table has continuation. Precast concrete or public T section with cast in place concrete. So it should be K. So in our class, we will focus on section A and section K. Okay, A is steel, K is precast concrete. Any questions so far? Not, let's continue. So now, after we know the cross sections, it's either for us now going to be A or K. We have to find the distribution factors for the table, and the tables are a lot. So there's going to be a lot of table. For example, here 4, 6, 2, 2, 2, B1. It says live load distribution factor for moment in interior beams. I need a volunteer to ask. Maybe Adam. Adam, are you online?
Yep.
Last time, do you remember when I did like a second session example that I start to move around you guys to help on answering the influence line and moving load? I asked you to calculate the moments, right?
Yep.
Maximum moment and the shear, correct?
Yeah.
And you were able to calculate it for any kind of girder, right? Just a girder that has a span in it, right? So if we calculate the moment or shear, in order to distribute them between the girders, we have a separate table for it. So we have table for moments to distribute the moment. Okay, so let's say you solved it last time, the moment was 1,000 kip per foot, right? And you didn't count how many girders in this example, right? You don't care about the cross section, right? Or transverse direction. Now the 1,000 here, we have to distribute it between the girders, okay? So in this table call clearly that this is a live load distribution factor for moment on interior girders, okay? And you see how ugly the equation looks like? So this table, in order to read it, it said, what is applicable cross section, right? A or I, A or L, L, A, E, K, whatever, right? So we are A or K, right? Because of the focus of the class, correct? Either steel or precast concrete, pre-stressed concrete, correct?
Yep. So
once you have those, and it's concrete deck, you go and you have this table. What is S, Adam? As it said, spacing between the girders, correct?
Yeah, the spacing. Yeah.
TS is the thickness, right? Of the deck. L is a span length, correct? NP is number of girders, and kg is the stiffness factor that we just discussed, correct?
Yep.
So in order to use this table, you have range of applicability, okay? So if your span is spacing more than 16 or less than 3.5, you cannot use the table. If it's the thickness is between less than 4.5 and more than 12, you cannot use the table. If your span is less than 20 or essentially not a bridge, if it's more than 40, you cannot use the table. If you have 4 girder or more, you can use. If less, you have to use this 3 girders. 2 girders are not allowed. kg is ranging between 10,000 to 7 million. So you need to, after you sketch your cross section, you need to come up with S value, TS value, L value, NP, and kg, and check them against the table. Okay.
Mm-hmm.
And after that, it tells you one design lane loaded, or 2 or more design lane loaded. Okay. The factor, the live load distribution factor, would be for one design lane loaded will be 0.06 plus spacing over 14 to the power 0.04 times spacing over the span length to the power of 0.03 times kg over 12 span length thickness to the power 3, all to the power 0.1, which is very nasty equation, correct?
Yeah.
But if you have those parameters, just plug it in, get your factor, right?
Mm-hmm.
And if 2 or more, you have another equation. It is very similar. Instead of 14, you got 9.5. The powers are different, right? And the constant is 0.75, 0.75 instead of 0.06. So if you get those numbers from your cross section, you just plug in, you get your live load distribution factor for moment, interior beams. In those tables that you got from AASHTO, they included already the multiple present factor. So the multiple present factor M, remember, for 1 lane, 2 lane, 3 lane, all those 1.2, 1 factor, 0.85, they are included. Yeah, so they are included, so you don't need to multiply already time those factors. Okay?
Yeah, is that the reason for the 0.06 and 0.075, I guess? Because it's the one design lane or 2 or more. It kind of just...
It's kind of, it's at the end, after they drive the entire distribution factor, okay? They multiply times 1.2, and they multiply here times 1. So it's not actually, you don't need to worry about it in this table. It's already implemented. Okay.
Yep.
Okay. So if we continue, there's going to be a series of tables. The second table, here the table moment interior, moment for interior beams. There is another table for moment exterior. I need another volunteer. The cycle, maybe Joe or Kyle. Joe?
Yep, I'm here.
So this one is moment and exterior girder, right?
Okay.
And we have section A or K, right? And you are using concrete bridge tack, correct?
Yep.
It says for one design lane loaded, use what?
Lever rule for all. Yeah.
So what we did already before, right?
Mm-hmm.
We need to use it here for one lane. Okay, so even the table here is calling for lever rule, correct?
Yeah.
For remember the DE value, the distance between the wheel and the exterior girder, GE, right?
Yeah.
We're gonna use it for 2 or more design lane loaded, okay? And there is a range for it. It can be negative 1 to 5.5. -1 means that your load is in this side. So this is a negative side, right? And this is a positive side. So if the load is an overhang, it's positive. If it's inside, it is negative, okay? Can you guess what is E times G interior? Joe.
Yeah.
So G is the distribution factor, the live load distribution factor, okay? Correct?
Yeah. So is there like a value for G?
So the G interior is the one that you have from the previous table, this one. Okay?
Yeah.
And you just, this is G interior, okay?
So you multiply that by
E, which E is 0.077 plus DE over 9.2.
Yeah,
Okay.
so if we know D, we can get E. And
Exactly. And you already calculate E interior, you got the light load distribution factor for moment exterior, correct? Any questions from anybody? I know those stuff are like more like we are figuring out as we go, right? I need another volunteer here, maybe Granny here is around. Who's actually online today? Let's see. Jean Cleary is online. Hello.
Yeah, I'm here.
Yes. So this one is a bit tricky. All the table that I showed for moment, interior and exterior, are for bridges without skew. So the bridge you have in the plan view, the bridge is having no skew, right? So the pier is perpendicular to the longitudinal direction, okay? In some cases, you can have the pier inclined. So this is the C theta value measured from the pier to the axis perpendicular to the longitudinal direction. Here is theta. So you have some correction that you need to do for moment factors based on this table. It's very complicated. Same, you still can use kg, L, TS, S, and L to calculate what's called C1, and your theta is this theta. You have a range of 30. If it's below 30 degree, you don't correct for it. You correct it between 30 and 60. And I do think that some of you will have the project with skew, but the skew will be 20. So you don't need to worry about it for a moment, actually. Joe, do you have any questions so far?
No, I don't.
Okay. Maybe Moira Smith.
Yep.
So we did the moment, right? Interior and exterior.
Yeah.
Now it's time for shear interior, okay?
Mhm.
So this table is telling you what? Can you tell us what this table can be telling us?
This is calculating the live load distribution factor for shear instead of moments, and it's for interior beams.
Okay. What kind of cross section we are always working on is either A or K, right? Steel or concrete precast, pre-stressed. If it's one lane loaded, you have two sets here. If you are having 4 or more girders or 3 girders, correct? If it's 3 girders, straight away use lever rule, okay? If it's 4 or more, make sure you check the applicability. This is the easiest equation, right?
Mm-hmm.
is 0.36 plus spacing over 25. And for 2 or more lanes, use 0.2 plus spacing over 12 minus S over 35 to square. And this will give you the shear on the interior beams. Okay. I think everything gonna add up once we do the practice problem, but pay attention with me, please. Maybe who's online? I just didn't get different person. William Crux. William, are you online? William. It's not. I think he's having problem with mic, maybe. Let me try to check. Juan, are you online, Juan? Not responding. Okay, so as okay, let me check. Maybe Abu Bakr.
Here.
Yeah. So this one is giving you the shear on the exterior, correct?
Yeah.
So the live load distribution factor shear exterior. Your case is always A or K, correct?
Yeah.
If you have one design lane loaded, you use what?
A lever rule.
And if you have 2 or more, you go back and see what is your interior live load distribution.
G interior, yeah.
From this one.
Yeah.
Right? And you multiply times E, but make sure that your E here is different than the moment. It's just 0.6 plus DE over 10. And if you are only 3 girders, use lever, right? Usually you will have 3 girders, minimum is 4 girders. And similarly, if you have a Q, you correct with this factor. Okay.
Yeah.
So let's go through the assumptions of these tables. I'm not sure how to. So for this table, the distribution of live load can be used for girders, beams, and stringers, which meet the following condition. So the table has applicability ranges for numbers, but it was based on those assumptions. The first one, the bridge width is always constant. So if you have a bridge span here, maybe 2 span bridge, in every cross section, the width should be the same. So assumption of this equation is the width is constant. Second assumption, unless otherwise specified, number of beam is not less than 4. Beams are parallel and has approximately the same stiffness. So if you have a plan view, as we're gonna know later when we do the project, let's say this is apartment 1, this is pier 1, and this is apartment 2. This is a plan view, and those are your girders. What's mentioned here is that beams has to be parallel, so you don't have like a beam that has different distance, has to be constant and parallel, right? And they always have the same very close stiffness, okay, or cross section. Unless otherwise specified, the roadway part of the overhang DE most likely to be 3 feet, not more than 3 feet. This is article that take care of if you have curved bridges. Cross section is consistent with one of the cross section that we mentioned in the table, which is A or K or H, whatever we discussed earlier. So this is actually a flowchart telling you what should you expect. If you solve for shear, you use your simplified equation for interior and exterior, right? And it tells you when you need to use lever rule, okay? For interior girder, for moment, you use also method 2, which is simplified equation. Exterior, you will have cases where you can use lever rule or equations or even method number 3, which is called special analysis or a special method. So you have lever rule, simplified equations, special analysis. The span L, if you have simply supported beam, is just going to be the span L. But also the code have a table for the span to identify for you the span. For example, if you have positive moment, let's say you have a 2-span bridge. Okay, your moment looks like that. So in the positive sections, your span is this span being under consideration. So span 1 will be for the positive moment here, and span 2 will be for this positive moment. Okay, and for negative, you will take the average of the 2 spans, because you will need to calculate for negative distribution factor for negative moment and for positive moment, etc. This is pretty much, I think moving forward, we just have examples that we will be solving. I just think so. So let's take 5-minute break and come just solving numbers, okay? Let's come back at 8:25 and we should conclude in 4 minutes. Okay, let's resume now. I think it's 8:25 now. This is a level roof, similar to what we discussed last time. So let's have all of you to start solving with me some problems. So I'll ask you, this is the case where you have a bridge. The spacing for this case was 16 feet, which is too high. I think it was for a very old example. I think they limited now to 15. And this is the exterior girder, and this is the interior girder. This is the location of your internal in your hinge. Okay. You start with 2 feet to put your first wheel, right? Of 0.5 p. Correct. And another 6 feet, you put another 0.5 p. And you have 4 and 2, which is give you 6 feet spacing to the first wheel of the second, and another 6 feet to the second wheel of the second truck. And this add up to 2 feet from the last load, fourth load to the interior, right? If I assume one loaded lane only, I have to assume that I only consider this one exist over the bridge, and this is not in existence. So can you guys start calculating for me, if you take the moment here for those 2 loads, how much will be your reaction here, or the distribution factor on the exterior girder? Just maybe solve it, and please include the multiple presence factor. M for one load is equal 1.2. So after you calculate, multiply times 2, 1.2. I'll give you a couple minutes to just work out this. We got few answers, so if I ask someone to help me, Mike Dusto, are you here? Mike? Who can volunteer? Where's Mike? I don't know. Kyla King, maybe? Are you here? Kyla, can you hear me?
Yeah, I'm here.
So let's maybe do it together, okay? So you have to only consider one lane loaded, correct? So you have to consider those loads, only the first two, correct? If I take the moment for the first wheel of the first truck around this hinge, how much will be? It will be 0.5 p times
2.
No, the distance from here to there, right?
So 20.
20, right? Plus the second one is 0.5 p, correct? And the
Yes.
distance would be what? From here to here, correct?
14.
14. And the reaction will be the distance between the two girders, correct? So RG1 will be times how much?
16.
16, correct? So if you do this, it would be 17 P equal 16 RG, right? 1. That will give you a number of 17 over 16, which is, I believe, 1.0625. And after that, you have to multiply times the present factor is 1.2, will give you 1.275. I think most of you got it correct. If I move the slides, I think I got it correct. After that, I multiply times the multiple present factor. I got 1.275 p. 1.275. If I want now, maybe I have another student with me. Zach is here.
Hello?
Can you hear me, Zach?
Hi, yes.
So now I need you to count for two lane loaded. Lane loaded mean that you have to consider all the 4 wheels, right?
Right.
Around this hinge, correct?
Correct.
So can we do it together? Like the first wheel here is the same as before, right? 0.5 p times 20, correct?
Correct.
This distance from the hinge to the first one is 20, and plus 0.5 p times 14, similar as before, correct?
Right.
What about the third wheel? It's gonna be 0.5 p plus what? Times what?
Where would
Times
it be from like just the side section there? Like the
from here to there, right?
Yeah.
How much is that?
What is that? That's a 6 in there, right?
6 plus
Plus 2. I couldn't read the number.
8, right? And 0.5 p, the last node is what? A distance of 2, correct?
Right.
Did you notice when you start at 20, right? You always decrease by 6. Right?
Right.
Because the distance between the wheels at 6, right? So if you want to solve it very fast, you just look at the first one and keep adding 0.5 p times the same distance minus 6 minus 6 minus 6, correct?
Correct.
And this should be equal 16 R G1, correct?
Right.
And this should give you, if you solve it, 1.375, correct?
Right.
And the multiplication factor is 1. So you don't need to work for it. It's just 1 times 1.375. Now you have two cases, right? One lane loaded, right? One lane give you 1.275, correct, from the previous slide. And two lanes are more equal two lanes, right? They give you 1.375, right?
Mm-hmm.
Which one you should use?
The 2-lane, right?
Yeah, because higher. So the live load distribution factor is higher. Okay. Thank you very much, Isaac. Any question from anybody? So this is the live level rule, method number 1, correct? Now we need to do example on the simplified method. So I need more interaction from you. So we solve it together, okay? So this is a girder. The spacing between the girder are at 4 girder at 12 feet, okay? It's not exactly to scale, so pardon me. You have the edge of the barrier here at 2 feet from the center of the exterior girder. The overhang is 3.5, and you can put 2 feet to put your first girder. Sorry, first wheel load for the first truck. After that, you put 6. You could put 6 feet, and you keep adding loads for 6 feet. You know, for this example, you have first to count how many lanes you have, but we counted already before was 3 lanes that you are allowed to have. So you'll have P1, P2, 3, 4, 5, 6, all at 6 feet spacing. Okay. The given is that you have 4 girder space at 12 centers, 3.5 bridge overhang, out to out 43. So you have 3 lanes. A roadway accommodate 40 feet, right? So 3 lanes. And the thickness of the bridge so thickness of the cast in place concrete is 9.5, including 1/2 inch integral wearing surface, mean that your concrete is 9 and you have a wearing surface of 0.5. So the concrete part is 9 and the wearing surface is 1/2. Okay, concrete. So 9.5 include 9-inch concrete and 1/2 inch wearing surface. The concrete, if prime C is 4 KSI, the area of the girder is 72.25 inch square, and the moment of inertia of the girder is 62.658, 62,658 inch to the power 4. We need to calculate the live load distribution factor for interior and exterior girders for moment and shear using simplified equation. So let's get started here. Maybe Jack, are you online? Jack Peterson.
Yeah, I'm here.
So you remember the stiffness parameter that we discussed, I think with you too, right? When we asked, like, we put the girder on smear it in the center of the bridge deck, right?
Right.
So this is the equation, correct? Kg equal N2 times 1 plus A times Eg to the power 2, correct?
Yeah.
I do believe they give you the value of Eg, I think, or not. The value of Eg is a centroid. I think it's somehow they calculated here. Let's calculate it together too. And you need to get N, you need to get I, A, Eg in order to calculate Kg, right? I is given, correct? 62,658. A is given as 75.25, right? So we need to calculate N and Eg. N is the modular ratio, correct? It's a ratio between modular elasticity of the steel girder to the concrete deck, and you can calculate the modulus of elasticity of concrete based on Ashton equation for 4 KSI, and the steel is around 29,000 KSI. You get it about 7.96. Get the integer is around 8, correct?
Yeah.
And the top part will be calculating EG, okay? So the EG is a centroid of the cross section to the centroid of the slab, right? So we need to calculate the centroid, the distance from the centroid to the top of the top flange is given as 39.63, or you have to calculate it as we did in homework number 3, correct? 9/2 is the concrete slab thickness, 9/2 to be here, right? This distance. The distance 3.5 is from the bottom of the concrete deck to the bottom of the top flange, right? And 1 inch is the thickness of the top flange, because you actually double count it, correct? I think, Jack, you have a question on this one, right?
Question on what? Like double? You said double counting?
Yeah. Why we are subtracting -1 inch? Or 1 inch from the equation. Or in other words, what is 9/2?
That gets you the center of the slab itself.
To the bottom of the slab, right?
Yeah.
What is 3.5?
That's the hunch. Or haunch.
Yeah. Haunch, yeah, haunch from the bottom of the slab to the bottom of the top flange, correct?
Right.
And the 39.63 is from the centroid of the steel girder to the top of the top flange, right?
Yeah.
If you see that we already counted this time and this time, right? So the flange is counted twice.
Yeah, I'm seeing it.
Yeah, so that's why you have to subtract an additional 1 inch from this calculation, give you 46.63, right? Within this equation, you got your kg as 1.8 million, and the applicability ranges between 10,000 to 7 million, right? So we are okay, correct?
Yep.
Thank you, Jay. Thank you. For this one, this is moment for interior girder, right? I need someone to help. Maybe Hamdi, are you here?
Yes, I'm here.
So, sorry for that. Our spacing is how much?
It was, I believe it 12.
12 feet, correct?
Yeah.
So are we passing this requirement? First
The
of all,
first one is okay.
you're using moment for interior, right? So first one is okay, correct? What is your TS?
Thickness of deck.
It was 9, right? 9 inches,
9.
right? Is this okay?
Yes, it is.
Yeah, okay. What is L? The span, right?
Span of bridge.
I think it was 140, okay? So we are okay too, right? How many girder would we have? Girders, right? The cross section was 4 girder, correct?
Yes.
So the kg is 1.8, 1.8 almost million, right? So we all satisfy all those applicability range, correct?
Yes.
For one design lane loaded, we take this equation as it is, put it here, put the spacing as 12, right? The span as 140, right? kg as 1.8 million, L as 140, T as 9 to the power 3, correct?
Yes.
You don't forget the powers and the constant. Trust me, until now, if I do this calculation 3 times, I get 3 answers on my calculator, okay? Because you're always gonna miss something. Okay,
I can see some numbers in inch or some numbers in feet.
Yes, yeah, this is a good question. So the way they build up this equation is your spacing and your span lengths are in feet. Okay.
Okay.
Your TS is in inches, your L is in feet, and your kg is in inch to the power 4, whatever they have. Okay. So this is built in the equation. Okay. Don't try to make them in inch or feet by yourself. You see the boundaries here, right? TS in inches, S in feet, L in feet. So don't, yes, it mix between them, okay?
Yeah.
This is good, very good observation, okay? What I usually try to do to avoid any problem, I try to calculate this parameter alone, okay? And after that, I do the calculation later on so I don't mess up with the calculator, okay? For 2 or more lane loaded, Hamdi, the second equation will be applied, right?
Yes.
So the only difference that you will have the constant different and 14 will be 9.5 and the powers will be 0.6 and 0.2, correct? In this case, you go for 1 lane loaded 0.528 and for 2 lane loaded 0.807, okay? Which one governs is 2
lanes.
Okay. Any question for anybody? Or should we choose another one? Then I guess I think I met some people not asking because they are hiding somewhere, maybe. Let me try to select maybe Evelyn. Are you here?
Yes, I'm here.
Yeah. So let's do the last one we did moment for interior, correct?
Yes.
Let me see. So this one is shear for interior, okay? Shear for interior. Okay. So we need to go for the table that has the shear for interior, right? And we are section A, correct?
Mm-hmm.
So for how many girders we have? 4 girders, correct?
4 girders, yeah.
The spacing is what? How much?
The spacing was
12 feet.
12 feet, yeah.
The span was 140,
Mm-hmm.
correct? And TS was 9, right? Inches, correct?
Yeah.
So for our case, we have 4 girders. So one design lane loaded will be just 0.36 plus S over 25, correct?
Mm-hmm.
S is now 12. You use this equation 0.36 plus 12 over 25. You got how many lanes?
0.4.
It's 4, right? For 2 or more, we'll use this one. only function of the spacing 12, right? So I'll give you 1.82, right?
And so that one's larger, that's the one that governs.
That will go, okay? So we did the interior, we did moment and shear, correct? Now we need to do what? The exterior. So this one governs, right? For shear. And this one governs for what?
Moment.
For moment. Okay. Let's do the exterior bending moment. Okay. Maybe I will. Alison, are you here?
Yeah.
Yes.
Oh.
Okay. For exterior bending moment, this is a table, right? We always go to the moment and exterior here, right? So make sure you use the right table, correct? Our problem, it has lever rule, correct? For one lane, or 2 lane, you used to have E value, right? And interior. So if you remember, this is your interior girder, this is maybe your exterior girder, right? This is your bridge deck. Oh my God, sorry for that. And you assume hinge here, correct?
Yeah.
And if you go back to the cross section, the first wheel was exactly at the exterior, right? So it was here, right? 0.5p, right?
Yep.
And this is 12, correct?
Yeah.
And the other one will be located where?
And
6 feet from first,
Yep.
right?
Yeah.
So can we calculate using lever rule the reaction here or the load here?
Yeah. If we treat the other one as like a hinge.
Yes, correct. You take 0.5 times
0.5 times 6. Times 12.
times 12,
Plus
right? Plus
0.5 times 12.
6, right?
0.5 times 6, sorry. Yeah.
Yes. Equals
R times 12.
times 12, right? If you do that, this is 6, and this is give you 6, this is give you 3, right?
Yes.
So R equal 9 over
12.
12, which is, you see it here, right? So 0.75, but you have to multiply times what? The multiple present factor, right? Because it's a lever rule, right?
Yeah.
So this confused. If you have a lever rule, you have to use multiple present factor. So it became 0.9, correct? What's 9 feet come from?
0.5 times 12.
It's just the addition of those 2 parts. 0.5p times 12 plus 0.5p times 6. Okay.
6 plus 3, 9.
Correct? Walter? Okay. Um, for the 1, 2 or more lanes, you have to go back to the interior moment. Where is the interior moment? Interior moment. Where is the 2-lane? 0.807. So you need to get it. 0.807. 0.807. And you need to calculate E, right? And E is 0.77 plus D over 9.1. And in this case, actually, DE should be 0, right? Because the load is exactly on top of the exterior. So please correct for me for this one. This should be 0. And this should be 0.77. So this factor should be 0.77. And this has to be modified. Okay, I'll fix it. But anyway, the one lane load governs. Okay. The last one is very similar. Shear for exterior, same lever rule. And the DE here should be actually same. This should be 0. So this should be 0.6. And this should be 0.6. And from the interior, the value was 1.082. Still, this is governing. So we actually came up with, at the end, you can have a table. And this table can summarize all the equations. You can say one lane or two or more exterior, interior. Let's say for a moment, correct? And you can put those numbers and see which one govern for exterior, which one cover for interior, which one go for moment and for shear, correct? Any questions so far? I'll not cover today the spatial analysis because I feel like I throw a lot of numbers on you today. So this will be covered on Monday, or it's already on the video recording already that I posted, but I will cover it next week for 5-10 minutes in the beginning. One question I need to ask you, it's a very challenging question. If you go back to, let's say, those equation, you find that all the interior girder has to go with 0.807, correct? For moment. So if I go back, I can say for moment, I put 0.807, right, for interior. Those are the factors, right? And for exterior, it became 0.9, right? Correct? This is for moment, right? This is a summary of our calculation. The interior girder got 0.807, exterior got 0.9, right? Of your truck or lane load, right? Can someone please add them up to me? Add all those numbers and tell me how much? $3.414, right? Okay, so I have a question, and whoever gonna answer it, he will get like good bones. We will agree on later on, okay? How many allowed lanes that we can have here? 3, right? Based on the width, we only have maximum of 3 lanes, right? After we did the distribution factors, and we add them up, they add up 3.414, right? How come? How come we have more than the 3 lanes that we designed for? Any clue or any explanation? It's not really to allow for factor of safety. For lever load, we had to factorize. Okay, no, not right answer. Until now, keep trying. Any others? Maybe, can you guys turn on the camera so I can have a discussion with you and turn on your mics? So turn the camera on, turn your mics. More does it have to do with the present factor? No. Different trucks in different state? No.
Is it because your distribution, you're loading, you're positioning it from the left side of the bridge, so it's not exactly symmetric?
You are close, but you are not 100% correct, but very close. So we calculated the factor, we add them up, right? We came 3.414. We only have either one lane loaded or two lane loaded or three, right? We don't have four, correct? So how come we got 3.41? Any do you guys see my slide or you see your slide?
Is it because of the multiple presence factor?
No.
Is it because the width of the deck isn't completely used?
No.
Maybe because we consider the critical case for the exterior beam, and at the same time, after calculating the factor, we also consider it for the other exterior beam, which it doesn't make any sense.
Okay, you are close, but you are like an inch close to the answer. Yes, but try to phrase it different way. I see people hiding, like Adam is hiding, Anthony's hiding, Juan is hiding, Isa's hiding. Any answer? Maybe Joe? Any? So let's make it easier for you guys, okay? When we calculated the exterior girder, right? Case, right? We placed one girder, right? So one truck, and we did the lever rule, for example, correct? Or the factors from the distribution factor from the tables, right? Those factors 0.9 and 0.807, 0.807, 0.9 will not happen concurrently. They are the maximum of cases, okay? So if you put the truck very close here, you are essentially loading the first two, but the others are zero, correct? In the same scenario, correct? So those numbers are the maximums of scenarios. They should not be added up, because one happen when you load all the truck closer to interior, so the exterior will not see much. Okay? When you move the truck to the exterior, the interior will not see much. That's why those factors are the maximum of different scenarios. They will not happen same time. That's why we should not add them in the first place. Okay? So make sure that what we try to do today is to get the maximum effect of the trucks on the exterior girder and interior girder. No one scenario will give the maximum on the two of them at the same time. Okay? Make sense? Okay. Any questions before we adjourn? Actually, I have some notes for the homework. Let's go through them. Did you guys submit your homework online or not? I didn't see much submission today. Did you guys really submit it? So go ahead
What
and
does it tell you? There's like a different way to go on and get to that website, by the way.
let me show you what I get, okay?
In the bridge animation thing, you know how it wasn't working before?
Yeah, the bridge animation, you don't need to use it. You just need to calculate the area by hand. That's the
But
easy.
if you go to bridgeanimation.com, which is the original website, and
Okay.
then you click on software and click I'm not a robot, it'll let you in.
Okay, so the problem was because of this, I'm not a robot?
Yeah, that's why.
Okay, so I have to go to, okay, maybe that's why everyone
Yeah,
is
if you
saying,
go through it that way, go through the steps that way, you can use it.
okay, okay, sounds good. And it's good to catch. I don't know, I put the link, but looks like because I skipped the robot stuff, that's why it's not getting us the right stuff. So let me start to maybe how I don't, Walter, I don't want you guys to submit by email because it got missed. I receive 200 emails per day and I have to chase you back. So use Canvas, okay, to submit your homework. I still want to go back and show you okay. I need to go back to our homeworks. So you have another homework, which is topic number 4. This homework. For assignment 4. Assignment 4, I uploaded yesterday, so you should be able to see how it looks like now. The first problem is okay. The first problem is similar to what we solved in the class last week when we did. We have a span and we need to calculate maximum moment and shear using moving load and influence line concept for HS20, for design tandem, and for your state permit truck. If you're a state permit truck, you are muted. You are muted. Can you unmute yourself?
I'm sorry, I was talking to my son.
Yeah. Okay. Oh, sorry. I thought you were asking a question. Okay, so it's fine. So here, this is a problem related to influence line and moving load concept. The second problem is where I ask you to use Ashton equation to calculate how many. First, you calculate how many design lanes for this cross section, and live load distribution factor for moment, shear, interior, and exterior. And this is your cross section, similar to what we did today. This is the girder detail. Okay. And the last one is using bridge in problem number 2, using the special method, which we will cover next Monday. Okay. The due for this one is Thursday, March 9th. So it's almost 10 days from today. I'll be open for Friday. Okay. 10th, end of the day, should be fine too. But I want to make sure that you submit by that time because after that, there's going to be spring break, correct? And after the spring break, you will have the midterm on Monday, the following spring break. So I need to make sure that at least you see me on Thursday if you have something to ask about and double check your answers. So because some of the question will be covered for assignment 1, 2, and 3, and 4. Okay. Any other questions? Don't forget to submit online your homework number 3. And thank you very much for joining online. Sorry for missing in-person class. Hopefully it was fine today. So any questions? Have a good night, guys. Thank you. I'll post the video once I receive it from WebEx, okay? Thanks.
Have a good night.
Good one, Professor. Feel better.
Thanks, Professor.
Thank you.